And yes, it's basically the same thing on both sides. Expand which one you feel more comfortable using.
Did they use this in the army or
No. Okay, so guys, let's come back to this. Sorry. When we look at a periodic table, let's define these. The atomic number is the number of protons. Okay, so your atomic number is the number of protons. By the way, in order to keep things balanced, if protons have a positive charge and electrons have a negative charge, what do we know about the number of protons and electrons? If we're going to be balanced, what do we know about that? They have to be the same. Okay, your protons and electrons have to be the same number. So you guys look at your periodic table, okay, the big number that stands out, like for example, if we look at boron, what's the big number for boron that kind of stands out to your eye? Boron's kind of like in the third column. 5. So the atomic mass, so let's do boron for this. We're looking at boron. So our atomic number is 5. So that's our atomic number for boron. So boron is 5. Now, the atomic mass is that decimal number. So when we look at boron, what is our decimal value for boron? 10.81. Okay. All right. Now what that is, the atomic mass is the number of protons and neutrons. So here's the thing that gets kind of weird. The atomic mass is 10.811, and that really is an average of different numbers. We'll get into that later. A lot of times what we're going to consider for this course, since, kind of introductory science course here, we're often not going to worry about the 10.81. We're going to worry about the rounded value. So 10.81 can be rounded to what number? 11. So a lot of times you also hear that as the mass number, which is not the same as the atomic number. So the mass number is just the rounded value, so therefore 11. Now, what's important is if you know the atomic number and you know the mass number, you can therefore determine how many neutrons that boron has. So again, let's use a little bit of logic here. If we have an atomic number of 5 for boron, how many protons do I have? I have 5 protons. If my mass number is 11, what does that tell me about the number of neutrons that I have? I would have to have 6 neutrons. How did we get that? 11 minus 5. Take the mass number minus the atomic number. We now have the number of neutrons. All right, energy levels. There are 4 energy levels on the periodic table. And it's basically the electron shells. And what we have is we have an S shell, a P shell, a D shell, and an F shell. Hey, do me a favor. Let's go back to the previous page. How many electrons were we able to put in the first shell? 2. Hey guys, look at the first row of the periodic table. How many elements are in that first row? 2. Huh. Okay, take the next shell. How many electrons are in the next shell? Go to row 2 in the periodic table. There's 8. So that's how many the third shell is going to have. 8, because there's also, there's 8 there. Okay? So that the two rows there of 8, those are called the p shells. Okay, so we have one s shell, we have two p shells, then we have two d shells, and then we have two f shells. And the f shells, there's a whole bunch of electrons down there. They're very unstable. Think of it like Rome. Okay, as you go down the periodic table, they become less and less stable. It's kind of like Rome. You had this giant empire, and the farther that you expand your empire, the less control you have of those outer regions, right? All right, so what happens is the atoms actually break down because they keep losing their electrons. And that's called radioactive decay. Those atoms are literally decaying and becoming different atoms, different types of elements. It's just because that nucleus no longer has that attractive force on those electrons. There's just too many of them, and they're too far away from the nucleus. So it simply breaks down. Kind of simple to understand a little bit there. So those are your energy levels. The valence electrons are the electrons in the outer shell. These are the electrons that are used in bonding. So we really don't care what's going on in the inner. All we care about is the outer shell. Are we giving away electrons or are we taking in electrons? That's all that means. So when you're looking at bonding, all we're concerned about is the outer shell. Don't really care much what's going on the inside. All right, now it's time to talk about isotopes. There's ions and then there's isotopes. You guys in favor now? Here's the test question. Tell me the difference between an isotope. Tell me the difference between isotopes and ions. Right, there's the test question. Here we go. An isotope is when you have the same element. So the same element, but we have a different number of neutrons. So the same element, different neutrons. Think like this. That's for carbon 14. No. Ever heard of carbon 14 gauge? Yeah. Okay. That's carbon 14. That's an isotope of carbon. When we look at carbon, carbon's actual atomic mass is C12. So notice that we went from 12 to 14. So carbon 14 has 2 extra neutrons attached. So we increase the number of neutrons. And so we look at the atomic mass. Remember we said I was going to come back to this? The mass of an element is the average of the isotopes. And so it's getting a little bit deeper than what I really want to go into, but that's really what it is. When we look at those mass numbers, we're like, why are they decimal? Well, that's why. It's an average of all the isotopes added together. And we get 10.8 or for boron. And we look at carbon, the average is 12.011, which is basically carbon 12. Okay, so that's an isotope. When we look at ions, which is not on my list up here, an ion is the same element but we have different numbers of electrons. So it's whenever we gain or lose electrons, we get an ion that comes out of that. Ion is whenever we gain or lose electrons. So let's go back to our previous page again. All right, how many electrons did we have here originally? All right, so how many electrons is that total? 12. Okay, so which element is that? No. Okay. Guys, what do you know about the number of electrons and the number of protons? Have to be the same. Protons and electrons have to be the same, right? So if I have 12 electrons, how many protons do I have? 12. And the atomic number is number of protons. So guys, if I want to know what element I have, I need to go to the element that has 12 as an atomic number, and that is magnesium. Okay, so we've got Mg. Alright, so right here, Mg is our electron, or is our, is our element. And here's the ion. This is where the ions come into play. Remember we said earlier, what's easier? Bring in 6 more electrons, or get rid of 2?
Get rid of 2.
Get rid of 2. Okay, so now I want you to notice, when we get rid of those 2 electrons, right now we're sitting at positive 12 protons and negative 12 electrons, right? So our net gain is 0. Pretty happy. But again, we're not really happy because we want to have a full outer shell. So magnesium tends to get rid of those 2 electrons and basically transfers those off to another atom or another element. When he does that, that changes my number down here. All of a sudden, I no longer have 12 electrons. How many electrons do I have? 10. So what's my total charge? 2. So magnesium plus 2, that's your ion. And now we have an ion. Now I know you guys can't really see this that well, but up front, we have our Hoffman apparatus. Lots of big words being thrown around today, lots of cool names. Alright, all this is just water, a little bit of salt, and I have a battery. You might want to stick your finger in there?
Yeah, I'll stick my tongue on it.
I'll let you guys do that later.
Okay.
Alright, well what I'm really doing here is I'm sending an electrical current through the water. So what does that do? It splits the water molecules. And it splits it into 2 different gases. What are those 2 gases? Hydrogen and oxygen, right? Notice that one of these tubes has more gas in it than others. You can see that right here. So that was really far down from water. This one has just a little bit of water, or just a little bit of gas here at the top. H2O. There's 2 hydrogens for every oxygen, right? So what I'm literally doing right now is I'm taking the water and splitting it into the 2 ions. Ions of oxygen and ions of hydrogen. And that's these little bubbles you see bubbling up from the side here. You guys might not be able to see those in the back. But what's happening there, those little tiny ions, the hydrogen gas is being produced in the water, and then those hydrogens bond together and we get H2, which is pure hydrogen. And actually we're going to blow this up later.
We're gonna what?
Today? And we're going to light the hydrogen gas on fire.
Yes.
Yeah.
That'll be kind of neat, okay? So let's keep moving. Alright, so